Unit 5 Review. The purpose of this video is to review the topics in Unit 5. Unit 5 focuses on the internal loads in beams. There are two internal loads in beams, shears and moments. We can determine the shear and moment in a beam using the direct equation method or using the graphical method. Use the time shown to jump to a specific topic. First, a little background. Prior to beams, we learned about axially loaded members and torsionally loaded members. With both of these types of loading conditions, it was sometimes useful to plot the internal axial force or internal torque in a graphical form, or write them as functions of distance. In both cases, there was only a single internal load, internal axial force or internal torque. In both cases, the internal loads were equal to the accumulated sum of the external load. Transversely loaded members, also called beams, are somewhat more complicated. Beams are subjected to two internal loads, shear and moment. In a member subjected only to transverse loads, there is no axial force, so the internal normal force is zero. Before I go further into the review, it is useful to mention the sign convention that we use in our course. Our sign convention states that for distributed loads, positive is up. For internal shear forces drawn on a cut surface, if the beam is on the left side of the cut, the internal shear force is positive downward. If the beam is on the right side of the cut, the internal shear force is positive upward. For internal moments drawn on a cut section, if the beam is on the left side of the cut, the internal moment is positive counterclockwise. If the beam is on the right side of the cut, the internal moment is positive clockwise. Note that the internal shears and internal moments on either side of the cut are equal and opposite. There is a relationship between external distributed loads, internal shear, and internal moment. The relationship is shown here both graphically and with equations. For the simply supported beam with a uniformly distributed load, a diagram of the internal moment has the shape of a parabola, and the equation that defines it is a quadratic equation. A diagram of the internal shear and the equation that defines it is linear, and it is the derivative of the moment. In other words, the shear is the slope of the moment. A diagram of the distributed load and the equation that defines it is a constant. In this case, negative because the load is acting downward. The distributed load plot and the equation that defines it is the derivative of the shear. In other words, the distributed load is the slope of the shear. Another way to look at it is that the shear is the indefinite integral of the distributed load, and the moment is the indefinite integral of the shear. When deriving the shear from the distributed load function, or deriving the moment from the shear function, one needs to be aware of possible constants of integration. Let's look at finding functions for equations for internal shear and moment using the direct equation method. Here's a beam with several external loads applied. Suppose I want to find equations that define the internal shear and moment between points B and C. First, we should note that the equations for shear and moment from A to B are different from the equations for shear and moment from B to C. This is because there is a discontinuity at point B, where we transition from no external load on the left to some external load on the right. Whenever we have a discontinuity between endpoints of our beams, we have to section the beam at the discontinuity and find the unique shear and moment equations for each section. Now, the first step to finding shear and moment equations is to draw a free body diagram of the full beam and find the support reactions. The next step is to make a theoretical cut in the beam at a distance x from the support. The cut is always perpendicular to the beam axis. Notice how the x-axis has been defined for us. It is critical to know where your x-axis is so that you know how to define the dimension x. I recommend that you always dimension x from the axis origin to the point of the cut. Next, draw a free body diagram of the cut beam. Include all external forces, including support reactions. Also include the internal shear and moment arrows on the cut surface, drawn with the positive sign convention. Note that I have defined them as functions of x. This is because their values change as the dimension x changes. Also note, the dimension x in the figure is for the cut beam's full length, not from point B to the cut. With the dimension x identified, I can find the dimension from point B to the cut. It is x minus 1.5 meters. The next step is to solve for the internal shear and moment in terms of x. To find the internal shear, sum forces in the y direction to 0. To find the internal moment, sum moments to 0 about the cut point. Let me mention a few other notes you should be aware of. First, know that you can always check your shear and moment equations. For example, here are the equations for the internal shear and moment from B to C. I have clarified that these equations are from B to C with the limits shown. Note that the shear function is equal to the derivative of the moment function. This relationship always exists. Also, we know from using the graphical method for drawing shear diagrams that the reaction Cy should make a plot of the shear go to 0 at point C. This means that the internal shear at point C must be equal to negative Cy, or negative 4.875 kilonewtons. If we plug in x equals 4 meters into our shear equation, which corresponds to point C, then it returns negative 4.875, which is what we expect. Using similar logic, we know the internal moment at point C should equal 0, since it is the end of the beam and there is a roller support there. If we plug in x equals 4 meters into our moment equation, then it returns 0, which again is what we expect. Essentially, we check our answers by confirming the values for internal shear and moment at known points. The second note is that you can use the beam section on either side of the cut. Just be aware that doing so does not change the x-axis. Note how in the figure the dimension x is still measured from the axis origin to the point of the cut. So the length of the cut section is the total length minus x. Here, 4 meters minus x. Also note that I have included the internal shear and moment on the cut surface using the positive sign convention when the beam is on the right side of the cut. So here's an example problem where we have a beam with a bunch of loads on it, and we are asked to find the internal shear and internal moment as functions of x for section BC. And we see in our beam we have a pin support at A and a roller support at C and an overhang cantilever section from C to D. Now the first thing I'm going to do is draw a free body diagram and get my support reactions. So here's my free body diagram, and if I sum moments at point C and include all of the loads, I can solve for AY, and I get that it is 2.3 kilonewtons. Came out negative, so it is actually acting downward. And now, summing forces in the y direction, I find that Cy is equal to 9.3 kilonewtons. Came out positive, so it is acting upward. The next step is to make a theoretical cut at some point in my beam between B and C and draw a free body diagram of the cut section. Okay, so I've drawn a free body diagram of the cut section, and I need to have an x-axis so I can get a function in terms of x. So I've decided to define an x-axis originating at point A on the beam and pointing to the right. In the problems you'll get in this class, the x-axis will be defined for you. When I make the cut, the length of my cut then is the dimension x. I know from A to B it is 1 meter, and that means from B to the point of my cut, that's going to be x minus 1. On the cut section, I also need to show my internal shear and moment. I draw shear going down because this is the positive shear using our sign convention when we cut a beam and the beam is on the left side of the cut. We draw the shear arrow down. The positive moment, based on our convention, is that the moment on the cut is counterclockwise. Now we can solve for shear in terms of x and moment in terms of x by summing forces and then summing moments. When I sum forces in the y direction to 0, I will have negative 2.3 kilonewtons. That's the support reaction at A. Then we have a section of our distributed load. It's 2 is its magnitude, acting downward, so negative. And the length of the load is x minus 1 meters, because as x changes, that dimension changes. And then minus our shear, v of x. We show it down because we're assuming up is positive for our equilibrium equation. We set it equal to 0. And now we just need to do a little algebra and solve for this equation in terms of shear. Okay, and now I have the shear function in terms of x. And this is good for x going from 1 meter to point C, which we see is at 2.5 meters from the origin. And I can check the equation. One thing I could do is I could check, is dv dx, the derivative, equal to the distributed load? And if we take the derivative, we get that it's equal to negative 2. And notice our distributed load is, sure enough, 2 pointing downward, 2 kilonewtons per meter. So the derivative of the shear is the distributed load. And that's what we expect to see. There's another check we could perform. If we were going to plot the shear diagram, at least for a little section of this beam, we would know that it's going to drop down to a negative 2.3 and then stay constant for a little while from A to B, and then it's going to start to go down at a slope of negative 2 kilonewtons per meter. So I could check this point. When we evaluate our equation at x equals 1 meter, it should give us negative 2.3. Let's check it out. And sure enough, it does. So our equation works for this point B. And if we wanted to, we could continue this on and check it at point C, but I'm pretty confident that this is correct. Now I'm going to find the function for the internal moment in terms of x. And I'm going to do that by summing moments about the cut. Okay, so here's my moment equation. The first term is our support reaction at AY. It's 2.3, and the distance from the cut, where I'm summing moments, is the distance x. Then minus 5, because we've got our 5 kilonewton meter concentrated moment being applied. And then we've got our distributed load. So make sure you get this clear. The resultant force, or the magnitude of our load, is the area under the distributed load. So that's going to be the first two terms. 2 is the height, 2 kilonewtons per meter, and its length is x minus 1. And then its moment arm location from the cut is half the distance x minus 1, which, so I have it as x minus 1 over 2. And then I add on our moment, which is acting counterclockwise, positive m of x, and set it equal to 0. And now I just need to do some algebra and simplify this, set it equal to m of x, and I'll have my equation. I find it makes my algebra easier if I pull the 2 out and put it with the 2 in front here. That's nice because those both cancel each other out. And now what I'll do is I'll just FOIL those two x minus 1 terms. Now I leave m of x on the left side of the equal sign, and I move everything else to the right and change their signs. And now, simplifying, I have my expression for the internal moment in terms of x. And the first check I'm going to do is take its derivative. If I take the derivative of the moment function, does it give me the shear? In this case, yes, it does. What it doesn't check is that constant right there at the end of my equation. It doesn't check to see if that is right or not. Another way to check this problem is like we did with the shear equation, is we can check at the moment at a known point. And to get the known point, I can either cut it at a point and then solve for the internal moment. Or what I've done here is I've just drawn a section of the shear and moment diagrams from A to B so that I could get a value for the moment at point B. Like I said, I could always also just cut the beam at point B and solve for the internal moment right there at that cut. But I get that from the shear diagram and moment diagrams, I should have a moment of positive 2.7 kilonewton meters at point B. And I'll check that then by plugging in x equals 1 meter into my moment equation. And when I solve the equation for x equals 1 meter, I get that it is equal to positive 2.7, and thus it confirms what I expected to get. So I'm really confident that my shear and moment equations are right. Now, let's look at finding internal shear and moment along the length of a beam using the graphical method. With the graphical method, we take a free body diagram of a beam and directly draw the shear diagram and then the moment diagram using a set of rules based on the relationships between external loads, internal shear, and internal moment that we have previously reviewed in this video. Here are the rules. For a distributed load, the derivative of the shear, or slope of the shear diagram at a point, is equal to the distributed load, both magnitude and sign, at the same point. This also means that the change in the shear diagram between 2 points is equal to the integral of the distributed load, or area under the distributed load, between those 2 points. Next, the derivative of the moment, or slope of the moment diagram at a point, is equal to the shear diagram, both magnitude and sign, at the same point. This also means that the change in the moment diagram between 2 points is equal to the integral of the shear, or area under the shear diagram, between those 2 points. For point forces, we get a jump in the shear diagram in the direction of the force and equal to the magnitude of the force. For point or concentrated moments, we get a jump in the moment diagram equal to the magnitude of the moment. The direction of the jump in the moment diagram will be discussed further in just a bit. Let's now review the application of these rules through some examples. Let's draw the shear and moment diagrams for the beam shown. The first step is to find the support reactions. Here they are. Now I set up my coordinate system for the shear diagram. The units are the force units for the problem, in this case kilonewtons. My length units will be in meters. I know interesting things will happen in my diagram at points B and C. C is the end of the diagram, and B is a point of discontinuity. Now, we draw the shear diagram always working from left to right because the rules are based on working left to right. So start at point A. We have a point force and a concentrated moment. We ignore the moment. It has no effect on the shear diagram. That is not entirely true. The moment affects the support reaction forces, so its influence is felt through the support reactions. So next, we look at force AY. One rule is that we see a jump in our shear diagram from a point force. The jump is equal to the magnitude of the force, 5.125 kilonewtons, and is in the direction of the force, the positive direction. Here it is. Between points A and B, there are no applied loads, so our shear diagram remains constant over this section. From points B to C, we have a uniformly distributed load applied acting downward. One rule states that the change in shear between 2 points is equal to the integral of the distributed load between those points. So the change in the shear diagram between points B and C is equal to the area under the distributed load, which is a rectangular area. It is negative 4 kilonewtons per meter, because it is acting downward, times 2.5 meters. So we see a change of negative 10 kilonewtons in our shear diagram between the 2 points. Since we are starting at a positive 5.125 kilonewtons at B, we will end up at negative 4.875 kilonewtons at point C, like this. Note the application of the rule that the derivative of the shear, or slope of the shear diagram, is equal to the distributed load. Since the distributed load is a constant negative 4 kilonewtons per meter, then the slope of the shear diagram is also constant. In other words, it is linear with a slope of negative 4. At C, we have another point force. So the rule is, we see a jump equal to the force. The force is positive 4.875 kilonewtons, which jumps us up to 0. The fact that we ended at 0 gives us confidence that we did it correctly, because we always want to end at 0. Any point where our shear diagram crosses the x-axis is of interest to us because it is a local maximum or minimum point in our moment diagram. So we need to know the location of the zero shear point. Here I want to find the dimension x. Note that between points B and C, the shear diagram can be defined by a linear function. If I place a coordinate system with the origin at point B, then I can define the shear diagram as y is equal to the y-intercept, 5.125, minus the slope, 4, times x. The line crosses the x-axis at y equals 0. So I set the equation equal to 0 and solve for x. I get x is 1.281 meters. And I can then calculate the distance from the point of zero shear to point C. And my shear diagram is complete. Now I can create my moment diagram. I know that interesting things happen at B and C. I also know that the point where the shear diagram goes to 0, I will call it point D, is an important point on my moment diagram. Again, we work from left to right. At point A, we have a concentrated moment applied. We have a rule, that is, we get a jump in our moment diagram when we have a concentrated moment. So we have a jump of negative 8 kilonewton meters. And it looks like this on our diagram. The fact that we jump downward from a counterclockwise moment sometimes causes confusion to students. Let's pause this problem and look at this a little more closely. Here is the rule that can be memorized or reasoned out. For clockwise moments, we see a positive jump in our moment diagrams. For counterclockwise moments, we see a negative jump in our moment diagrams. I show a simply supported beam with a single concentrated moment acting at its center. When the moment is clockwise, the support reactions point down on the left and up on the right. This results in a shear diagram that is negative over its whole length. This makes the moment diagram always be sloping downward. Therefore, a positive jump in the moment diagram is needed to ensure that the diagram starts and ends at 0. The opposite is true for the clockwise moment. There is perhaps an easier way to remember this rule, and I call it the Mario rule. Suppose you have a counterclockwise concentrated moment acting on a beam. Suppose Mario is running along this beam. When Mario gets to the concentrated moment, it knocks him straight down. If Mario goes down, then the moment diagram goes down. Now imagine a clockwise concentrated moment acting on the beam. Here's Mario. When Mario reaches the moment knocks him straight up. If Mario goes up, the moment diagram goes up. The summary: a counterclockwise concentrated moment causes a vertical downward jump in the moment diagram. A clockwise concentrated moment causes a vertical upward jump in the moment diagram. Back to our example. Note that there are no more concentrated moments on our beam, so we no longer need the free body diagram. The rest of the information we need will come from the shear diagram. From A to B, we have a constant positive shear. We have a rule that states that the change in the moment diagram between 2 points is equal to the integral of the shear diagram between the 2 points. So the change in moment between points A and B is equal to the area of the shear diagram between A and B, which is a rectangle of height positive 5.125 kilonewtons and length 1.5 meters. The change is about positive 7.69 kilonewton meters. Since our diagram at point A is at negative 8, we will end up at negative 0.31 kilonewton meters at point B, like this. Note the application of the rule that the slope of the moment diagram is equal to the shear diagram. So the slope of the moment diagram from A to B is constant, or the shape is linear with a slope of positive 5.125. Now, between points B and D, we again use the rule that the change in the moment diagram is equal to the integral of the shear diagram. From B to D on the shear diagram, the area is a triangle. So we will get the area as 1/2 times the height, positive 5.25, times the base, 1.281. We get a change in our moment diagram of about positive 3.28 kilonewton meters. Since at point B, our moment diagram is at negative 0.313, we will end up at positive 2.97 at point D. Here, the shape of the moment diagram is parabolic. We can determine that it is concave down using the rule that the slope of the moment diagram is equal to the shear diagram. At point B, the shear diagram is equal to positive 5.125. So the slope of the moment diagram is also positive 5.125. As we move to the right towards D, the shear diagram stays positive but decreases in magnitude. So the slope of the moment diagram stays positive but becomes flatter. At point D on the shear diagram, the shear is 0. So on the moment diagram, the slope at D is 0, or horizontal. The shape must be concave down. To finish our moment diagram, we again use the rule that the moment diagram is the integral of the shear diagram. From points D to C on the shear diagram, the area is a triangle. So the area is 1/2 times the height, negative 4.875, times the length, 1.219, which gives a change from C to D of negative 2.970 kilonewton meters. Since we are starting at 2.97 kilonewton meters on our moment diagram at D, then the change takes us to 0 at C. This is exactly what we expect to see. Since there is no concentrated moment at point C, the diagram should end at 0 at point C. The shape is again parabolic and it is concave down. We start at D with a 0 slope and end at C with a negative 4.875 slope. Now our shear and moment diagrams are complete. Remember that one of the main purposes for drawing shear and moment diagrams is to find the maximum internal loads and where they occur. Our maximum magnitude shear is 5.13 kilonewtons. Our maximum positive moment is 2.97 kilonewton meters, and our maximum negative moment is 8 kilonewton meters. Let's consider one more example with a triangular load. These can sometimes be confusing to students new to the topic. Here is a simply supported beam with a triangular distributed load over its full length. Below is a free body diagram showing the support reactions. The shear diagram for the beam is shown. We find the change in shear from points A to B using the rule that the change in shear is equal to the integral of the distributed load. Here, the area under the load is a triangle. So the change in shear is equal to 1/2 times the height, negative 2, times the length, 6. We get negative 6 kips. So the shear diagram goes from positive 4 on the left to negative 2 on the right. It is concave up, which we determine from the rule that the slope of the shear is equal to the distributed load. At point A, the distributed load is negative 2, so the slope on the shear diagram at A is negative 2. As we move from A to B, the distributed load stays negative and the magnitude decreases linearly. On the shear diagram, the slope stays negative, but gradually becomes shallower. At point B, the distributed load is 0, so the slope of the shear at point B is also 0, or horizontal. The point of maximum moment for this beam will be at the point where the shear diagram goes to 0. That means we need to find where that point is on the beam. For this problem, it will be easier to find the distance from point B to the 0 point, as I will show. We will use the rule that the change in shear between 2 points is equal to the integral of the distributed load. The change in shear, delta V, over the distance x is shown on the diagram. This is equal to the area under the distributed load, over the distance x. This area is a triangle, so we can set the integral equal to the area of a triangle. The base dimension of our triangle is the distance x. The height of our triangle is unknown, but somewhere between 0 and 2 kips per feet. We can write a relationship for the height in terms of x. The triangle that is the shape of the distributed load is similar to the yellow highlighted triangle. So, using similar triangles, we can say that the height, h, is equal to 2 over 6 times x. Plugging all of this into the equation above, the change in shear has a magnitude of 2 kips, the base of the triangle is x, and the height is 2 over 6 times x. Solving for x, I get about 3.46 feet. With the length from B to C known, we can find the length from A to C. Here's the moment diagram for the beam. Note that it begins and ends at 0. From A to B, where shear is positive, the moment diagram increases. It peaks at point C. Where the shear diagram is negative, the moment diagram decreases. For the moment diagram to begin and end at 0, the area under the shear curve from A to C must be equal to the area under the shear curve from C to B. To get the magnitude of the peak point on the moment diagram, we will use this rule. The area under the shear diagram from B to C is easier to calculate than from A to C. The exam reference material has several geometric properties, including this one. It gives the area of an exaparabolic area, shown in blue, as 1/3 of the area of the bounding box, A times B. This means that the yellow region in the bounding box is 2/3 times A times B. This is how we can find the area under our shear diagram from B to C. Note that this area relationship only applies to a section of a parabola that has 0 slope at the corner of the bounding box. We have that at point B. Note that we cannot apply this area relationship for the shear diagram area A to C. This is because there is no point of 0 slope in that section. So I calculate delta M is equal to 2/3 times the length of the bounding box, A, which is 3.464 feet, times the height of the bounding box, B, which is -2 kips. We get -4.62 kip feet. The negative sign means that the change from C to B is -4.62. To end at 0, point C must be +4.62 kip feet. And now our moment diagram is complete. This concludes the review of topics from Unit 5.